pioneering founding father of Hack in the Box captured the flag. He's been in the computer security industry for the past 5 years, previously a system architect at Scan Associates. Having been involved with the organization of Hack in the Box security conference for the last 3 years, he ran the popular Capture the Flag hacking competition. And in the past 5 years in the industry, he has been involved in various aspects of computer security, including penetration testing, software and product development, training, network defense, system administration, and as well as being a freelance consultant. He currently runs a startup company that develops vulnerability and patch management software. His fellow presenter today, who will make his way on stage shortly.
Good morning, everyone. First of all, thank you for coming to HITB 2009, and thanks for attending this talk. Initially, the idea for this talk was supposed to be lab sessions where we will walk through analyzing packet captures and extracting evidence for network-based forensics, but unfortunately, the arrangement has been changed. So instead of 2-hour hands-on lab sessions where you will be able to participate as well, but so it's been turned into what do you call this, a presentation. So without wasting more time, let me begin. Anybody here performs network forensics or forensics in general? Raise your hands. No? 1, 2, 1, 2. Okay, so what is network forensics? There are a few definitions of network forensics. The first one is on the screen. So it's basically the use of scientifically proven techniques to collect, fuse, and identify, examine, correlate, analyze, and document digital evidence from various sources. Okay, this is the definition from Gary Palmer, and according to security expert Marcus Renham, network forensics is basically the capture, recording, and analysis of network events in order to discover the nature of security attacks or problem incidents. And according to Simpson-Carpingel, there are 2 types of network forensic systems: cache it as you can, in which all packets traversing through the network are stored and analyzed later. Or you have something that we are all quite familiar with, which is IDS model: stop, look, and listen, where every packet is inspected for malicious contents. And basically, network forensics is about monitoring, determining whether there's any anomalies, and determining the nature of attacks, if any. So you can think of it in a scientific approach, based on all these terms, or you can think of it as analyzing recording, CCTV recording, for example. So in your house, you probably have a CCTV, and you capture whatever that's going on. Yeah. For example, in an office, people walking in and out, blah blah blah. And some of these activities, people walking in and out of the office, carrying stuff, moving things around, are legitimate activities. And network forensic comes when there's an indication of malicious activities. But it may not be malicious. It could be attributed to a customer complaint, and customer calls up to you and say, hey, I was trying to pay for my I was trying to buy a laptop from your company, and I found out that somebody else has been using my credit card number. Okay, so it doesn't mean that you perform network forensics for purely for intrusion or attacks. So what happens now is, in the real world, the investigator, the police or the guards, they will take a look at the CCTV and try to figure out what's happened. So they look at the frames, look at the audio, they look at the video. They're trying to identify who's the culprit, who comes in and out, and perform evidence from there, perform their investigation from there. So in network forensics, however, instead of looking at video recordings, you're looking at packets. So some of the tasks involved might be reassembling packets, extracting traffic contents, examining network flows, inspecting packet headers, and so on, right? So when you perform network forensics, or any forensics for that matter, especially for network forensics, you'll be asking, when a particular IP has successfully compromised the system. So you want to confirm that. You want to determine the duration of a HTTP sessions. How long is the session? Is it a long session? Is it a short session? If it's a long session, probably it's a file upload, a webmail activities, uploading files, sending files to webmail. If it's a long download session, it could be a download sessions. Which network protocol is used in attacks? TCP, UDP, ICMP, blah blah blah. What's the main attribute of successful data transfer in TCP, for example? So when you establish that, okay, this guy is transferring data to a external server or whatever, so how do you confirm it? What's the attributes? What's the main attribute of successful file download, upload in FTP connections? Successful download, upload, or even file delete in a SMB, in network shares, in Windows shares, for example. And so on, and so on. Okay, so these are the questions that you want to answer. So now, why network forensics? Okay, there's file-based forensics, there's host-based forensics, there's memory forensics. While network forensics, because it's tamper resistance, especially if you deploy it in a breach, if you're tapping the network in a tap or a breach mode. So this evidence will not be polluted or not be tampered with by the attacker, unless of course the attacker managed to get a hold of your monitoring infrastructure. Where else? You look at host-based forensics, log files can be deleted, files can be deleted, entries, timestamp can be changed. Where else? For network, it's tamper resistant. There's no performance impact on the endpoint. You're sniffing the network, you're monitoring the network, and that's it. No management impact on platform. You're not running intensive programs or application or monitoring software on hosts or servers. It works across all operating systems because you're dealing only with pickup data or network flow. And you might be able to derive information that host-based might not provide. Say, for example, a file has been deleted from a disk, right? Or has been on a network share. So basically what happens is for a Samba share, when you delete the file, the Samba protocol will send will contain flags that indicate successful deletion. So you can confirm that you can look for that particular attribute in the network capture, and you can confirm, yes, there's a successful file deletion, there's a successful file copying, blah, blah, blah. So network forensics, you all know this, used for evidence recovery, same as host-based, same as mobile forensic, memory forensics. Here's an example that I've shown earlier, that I've talked about earlier. So basically, it gives you a lot of information that host-based forensic might not give, and it will also complement the host-based forensic investigator. Right, let's move on. So the process is quite simple. You capture, you record, and then you analyze, right? So the goal is to discover nature of intrusions and to complement host-based forensics. Now, let's talk about how maybe some MNCs or some companies do forensics, okay? So what they do, they get an IDS alert message, okay? So based on the alert, you go on and examine the event, okay? What's the event? Backdoor connection, TCP, Nmap scans, IE7 memory corruption, attack attempts, and then the analyst will perform packet examination. So look at the protocol header, for example, and based on the event, determine, okay, is this, does this confirm with the earlier indication that we get from the IDS, right? Followed by escalating the event to the appropriate channel, security response or incident response, and so on. However, what we've taught in the last two days of training, we use a different approach to network forensic analysis. Okay, so your alert can come from other sources, right? Customer complaints, for example, they cannot access server outage, service disruptions, right? So it's not necessarily security incidents. So if the network monitoring guys come to you and say, look, you know, our network is having congestion at the moment, you know, we can't go out to the internet, blah, blah, blah. So that could be part of your forensic investigation as well. And you determine the event's occurrence. Again, going back to the CCTV recording example. So customers say, you know, I think my purse or my bag or my notebook was stolen at this hour. So you go back into time and try to determine when the event occurred. And you analyze the sessions. So we're gonna explain more about what a session is in the next few slides, followed by examining the packets that you get, provided that you have monitoring infrastructure, and then escalate the events. And another thing that network forensic analysts have to keep in mind is that sometimes you need to examine the traffic payload as well, because it provides a lot of information, on malicious traffic. So the purpose, I think this. So for the new technique is to uncover malicious activities and then reconstructing of session data, reconstructing past network events, right? So basically network events already happened in the past. So you need to reconstruct, tell a story from it. Extract evidence. If you need to extract files from the packet capture, so that's the evidence. And if the traffic is encrypted or hidden, then that's part of the process. So here's the big picture. So there's the security analyst here on the left. The main box, the green box, basically explains or describes the process, not in order. So from the top, you have indications like IDS alerts or customer complaints, system or service outage, and then you get your evidence, the blue box. It could be a log files, it could be IDS alert files, and for this particular presentation, we focus more on packet capture. And you have the analyst. He as an analyst for network forensics, you need to have a few skill sets, which is in the yellow box, and then he goes on, looking at evidence and trying to discover the source of that particular incident. All right, so that's the introduction. Now you have a general idea of what network forensic is. So, so what do I use, right? So we always talk about tools, right? Everybody loves tools. So there's a lot of tools out there. And before we go talking about tools, one thing they have to keep in mind is that if you want to choose a specific tool for a specific task, okay, especially for network forensics, you have to ensure that this particular tool ensures data integrity. Okay, it will not pollute your, it will not pollute your evidence. It will not mess around with your evidence. It does not interpret, it interprets the evidence properly. Okay? You want to have, when talking about network, you want to have and you want to use a high quality protocol dissectors. For example, Wireshark. And you want to use data, or you want to use tools that can automatically reconstruct session data. So you want to, you don't want to do this manually. Something that offers the next point, tool that can offers high-level information about network events. Things like what's the top protocols, what are the distribution of packet size, whom are the top talkers, top communication, what is the most widely used protocols. And you also want to have tools that are able to extract files or useful contents from packet capture. So if you're dealing with payload data, if you're looking at, if you want to analyze the payload, you want to extract evidence from the payload, so you want to have tools that can do this as well. You need a tool that can replace sessions like Telnet, FTP, RSC, or IM messages, chat messages. And of course, we emphasize on free and open source tools. And again, usage of tool depends on your needs. So here are some of the open source toolkit. We would like to show you how to use it, but the 2-hour lab session has been reduced to 1 hour, so I'm just going to go through them, and so that you have an idea of the available network forensic tools out there. Explico is a network protocol analyzer. It's not a network protocol analyzer, but open source network forensic tools, right? So it offers port-independent protocol identification. What does it mean is that if you're running services on a non-standard port, okay, for example, I'm running SSH on port 80, so PIPI or PP chip is able to detect that particular service. Oh yeah, it's SSH running on port 80. It has solid TCP reassembler to extract application data, content from Picket files, supports logging to database, MySQL, SQLite, geolocation mapping, and many more. Here's some commands. You can run it in real time, and basically you can run it in real time and listen on the network interface, or you can run it offline. You can read a packet capture file, or you can specify a directory with, full of packet capture and decode it, and so on. So here's an example. It's a screen. Okay, screenshot. So you can see that you can load new packet file. It has columns. It has sections for HTTP, MMS, FTP traffic, email, and so on. Let's see a few more slides. Here is an example of emails extracted from packet capture. This was extracted by Explico. And the good thing is, like, this user interface, you can click and you can view the entire email in its entirety. You can view images. So again, you need a tool that able to extract image, able to extract files, and so on. Another interesting tool is PY flag. So PY flag is unique. Well, not really unique. It's interesting because it offers correlation with log source and file system memory forensics. So it's used for both host-based forensics, file system forensics, memory forensics, and also network forensics, and it provides a high-level analysis information. It has a protocol scanner to scan against PCAP file to reconstruct streams for different network protocols. And one feature that is interesting for a network analyst is the capability to index PCAP data. So indexing means that, okay, you have, I mean, if you're looking at files, PCAP files the size of 10 meg, 100 meg, you can do it manually. You can use TCP dump filter to filter out the packets of interest. But if you're looking about gigabyte of data, you're looking at huge packet data. So filtering them for the specific IP address, source or destination IP address or port, for example, will be it will take forever. So however, with indexing capability, you can search for a particular packet of interest very quickly. How they do it, you gotta read the academic paper on that. It's quite technical, interesting actually. Right. Here's an example of PY flag screenshot. Okay. This is it's a tree view. So you can see on the left is the source, destination, and then further down, if you click, you can see the stream and the decoded protocols pop, and you can see all the information, right? This is Amazon chat session extracted by PY flag. Hi there, buddy. What's up, man? I'm getting a new plan ready. You know, let's take over the world. Let's, you know, do whatever that we want to do. Okay, so that's PY flag. TCP extracts is a tool for extracting files from network traffic based on file signatures. So in forensics, there's this term that they use, which is called data carving. So when the forensic analyst, for host-based forensic analyst, tries to recover deleted files on the file system, so they use a technique called data carving. Basically, what it means is like extracting files based on the contents of the file, such as the headers, okay, and the or the footers. So if you do a hex dump on PDF file, for example, you will see %PDF -1.4 or -1.5, the version of the PDF document and stuff like that. So this file carving basically makes use of that particular headers and try to extract the files. Okay, so you can write file signatures. I don't have an example of file signatures here, but if you go to fileext.com, right, this website have a lot of information about files. Oh, I have it. Okay, so here's how you write TCP extract signature. The slides will be online, so don't have to. But basically, just explain a bit. The first two lines, you can see I'm doing a hex dump on a secret.pdf, and you can see the second one is super secret.pdf. So you see PDF. The common headers will be PDF dash %PDF dash 1.4.5, and another one is %PDF.1.4.9. So if you want to detect all kinds of files, so you need to look for this signature, right? So TCP flow, the goal is to construct different TCP flow streams in separate files for analysis, right? So if you have different, I mean, most TCP, most traffic will consist of different sessions, HTTP, MSN, BitTorrent, blah blah blah, chat. So TCP flow basically to construct different TCP flow, and it will be dumped in separate files for analysis. Another tool that we like to use is Chaos Reader. It can reconstruct network sessions like FTP, RSC, and replay the session. So you have a nice screen with the attacker or the user doing telnet to this server, and then what he keys in. As nice HTML report. So that's Chaos Reader. I'm sure you all use Wireshark and heard of Wireshark. Even if you don't use it, you probably heard of it. Wireshark has powerful filtering capabilities. It's very flexible for analyzing session data and application protocols. It can perform things like follow TCP stream, so you can see the connection, what is the communication between two endpoints. And the new version of Wireshark supports UDP stream. So the difference between TCP and UDP is that TCP is a session-based protocol. Okay, so because it's a session-based protocol, it's easier for you to follow the conversation, whereas UDP is stateless. The technique that Wireshark use is not to reconstruct the session. It's not by looking at the UDP headers, but rather going up into the network stack by looking at the application. So if I want to reconstruct a UDP session for DNS, I will look at the DNS protocol. So that's how they do it. So I think a few of you attended our training, and we use Network Miner. This is for Windows. Windows, again, it can reconstruct another session, and it can recover files. Do you have a screenshot? Yeah, we have a screenshot. Okay, so this is a screenshot of Network Miner in action. Okay, you can filter, you can search you can search on the at the application layer. For example, the payload of TCP and UDP packets. You can search the entire packet data. You can do you can search for a protocol that is not passed by Network Miner, and so on. Okay, so in the GUI, you see a few tabs. The list of hosts, the network frames, files that was extracted, images that was extracted, credentials, usernames, or password if it's in clear text, DNS queries, and so on. Fromos is another tool for extracting the file. Fromos works for host-based forensics as well as network packet. Okay, so this is an example of extracting files from Fromos. ClaimAV, when we extract evidence, when we extract files, unknown files, we need to run it against a virus scanner, for example. So you can use ClaimAV, or you can use any other antivirus software out there. Okay, screenshot. Okay, interesting files there, nude picture, stuff like that. All right, so let's move on to the next one. We're going to talk about the different kind of data that you can get from network traffic. The four common ones We call them network-based evidence. Statistical data, session data, alert data, and then we're going to move on to looking at application data, right? So statistical data provides a high level or general overview of network traffic over time, such as hours, days, weeks, months. Answer the question, okay, who are the top pair of destination IP and port? Who are the top talkers in the network? How much internet queries are we receiving in a day? Who downloads the most data? And so on. Okay. It's used to form a baseline to look for deviations. Okay. So one thing that we always emphasize is that it's far easier for you to investigate an incident if you are familiar with the familiar. Okay? So rather than trying to look for, rather than spending your hours, your time looking for like examining packets, decoding protocol, you'll be more productive if you know, if you're familiar with that particular protocol. In this case, it's network. So if you know that if you are familiar with your network environment, for example, you know that our SMTP traffic is always 30%. If it goes 40%, then it indicates something abnormal, right? So that's the idea here. If if you are familiar with a HTTP connection, for example, if you're familiar with HTTP protocol, you will be able to detect, it'll be easier for you to detect covert channel hidden in HTTP protocol, right? So always, try to familiar yourself with protocols, with your, with your network environment, okay? So that's the statistical data. It's usually used in a reactive manner. So I think that's particularly true for everyone. It's used for, when something jumps, when your graph jumps, go haywire and then you start doing something on it. The other data that you'll be interested to look at will be the network session. Okay, so, or network flow. Now, network flow is a set of traffic that is related to the same stream. Okay, it's equivalent to a call. When you're making a call to someone, hello, how are you? Let's go for a date, blah, blah, blah. Then you hang up, bye-bye. So that is one session, okay? So you have a start time and the last time and a few other information such as duration, how many bytes are transferred, and so on. The port, okay? So think of it as one communication between, one complete communication between two endpoints, right? So the start time, basically, usually the first packet in the flow. Some network flow tools have a different definition of start time and stop time or end time, okay? They may use terms like last time or they may use terms like end time, but we normally use start and last time, okay? And the last time, again, the last time may increase with the age of the flow and depends on the configuration of the flow meter. So, if you're using a software that analyzes flow and reconstruct the session, the flow session automatically, you got to know how it defines the last time. It probably have a configuration that says, okay, the start time, the duration should be 5 minutes, right, or 120 seconds. But So what happens is if you have a long session like HTTP download that takes about 30 minutes, instead of one flow, you're gonna get like six flows. Okay, so there's something to keep in mind. Going into semantics, session and flow. Session is conversion between two. Okay, let me go back. So you have one session, right? And then you have a flow. So in that particular session, you may have different flows. Now these flows again is defined by your network flow analysis tools. So like what I've mentioned earlier, so that 30 minutes is one session, but inside that particular sessions there are 6 flows. Okay, so that's the reason why is, like I explained here, the start time and last time is delimited based on the configuration of the flow meter. And then we have things like unidirectional and bidirectional flow. Unidirectional will be single direction, bidirectional will be both direction. Okay, so in this example, the top box is unidirectional. You see the direction from host A to host B, and the total bytes transfer is 50 bytes. The second one will be host B to host A. Host A returns, basically host B returns total of 100 bytes to both host A. So if you view the data in bidirectional, you will see the connection host A, host B, total bytes 150 bytes, source bytes will be 50, and the destination bytes will be 100. So here is unidirectional is one direction at a time, bidirectional is both direction at a time. Okay, and if you've heard of Argus, which is an open source tool for flow analysis, okay, it uses bidirectional model for flow generation, and you can convert the bidirection to uniflow output as well. And if you use Cisco NetFlow version 5, it's unidirectional. So you need to convert it to bidirectional to have a big picture of the particular network session. Yeah, I'm going to finish this up, then I pass it to him because I don't want to hog the microphone. So how do you perform flow analysis? If we have time, we will show you the examples later. So when you perform generic flow analysis, right, it's statistical and it's based on session. You don't look at the payload. There's no false positive or negative because you're looking at connections again. You don't care about the content or the payload of the packet. If there is a covered channel in that particular session, there's no way to fool flow analysis by using covered channel. A simple example would be looking at ICMP flows, right? So normally ICMP flows when host A pings host B, send a ping, the packet is normally 60 bytes. Okay, 40 bytes, 20 bytes of headers, and another 40 bytes of data. All right, so it's consistent. You will see if you filter the flow output and you look at ICMP, you will see a very consistent. The reply will be 60 bytes as well. Okay. Now, what happens if the attacker uses ICMP covered ICMP tunneling? Okay, you will see the size of the packets will vary. Okay, you will get small source bytes and very large destination bytes returned from the destination. So if you're an analyst and you look at this, you'll be like, how come the size differs from each, how come the size is not consistent? So this may indicate a covert channel through HTTP, right? It's encryption neutral. Again, we're not looking at contents. And of course, it's used for anomaly detection, DDoS detection, and network reconnaissance, etc. Here are some terms. I'm not sure I want to go through each of these, but you have the start you have the start time and end time, the length, total packets per flow. What's the summary of the data transfer, and you probably have the route info as well. Okay, these are the some of the basic metrics. If you're looking at IP, you're looking at source and destination IP and maybe TTL. If you're looking at TCP, going further down, you look at source and destination ports and TCP flags. So you can see the status of that particular flow, whether it's ongoing or whether it's completed, right, based on the TCP flags. For UDP, you can look at the source and destination ports. ICMP, you can look at type and code. So you can detect things like DOS attempt, worm activities, and port scanning in the flow. Why? Most of these types of activities will have high connection rate. So you will see a lot of flows, a lot of flows. The packet rate, for example, the connection rate and the packet rate, you can see a lot of packets from one source to another, from one source to many sources. Okay, so a sudden appearance of high packet rates linked to previous session with IDS alerts may indicate successful compromise. So if there is a machine on your network that suddenly starts to generate a lot of outgoing traffic, then it could mean that the box has been compromised, and now the worm is trying to infect or scan the entire machine, the machines on the network. So network scanning, right? Slow and single flows, for example, one flow to different ports or different hosts. You can see large sum of small flows to and from a certain IP address, right? Sync or TCP sync to a few IP address, a few ports, and the characteristic would be things like you will see a lot of RSTs, return RSTs from resets from the host, from the destination, because the port is not open, for example, or for TCP and SMB and port unreachable for UDP. So you can detect all kinds of network activities from flow. Again, worm. Okay, worms may scan backbone space. Okay, address space that are not used and should not be used. For example, payload may be downloaded from specific malicious sites. Source address is usually spoof, and each variant. So if you're looking at different variants of malware, most of them have identical payload size. Okay, they target multiple hosts, but only a single port on each host. So this is true for most of the worms. They may target one port or maybe two ports. Okay. Now, covert channel. I've explained about this. The purpose of the covert channel is, for the attacker to hide the tracks and also to bypass filtering or detection devices. if your network is very, very heavy, then it's very, very difficult to track. Okay, it's carried over well-known protocols, and there are long flows and there are short flows. For example, in S-lookups in the covert channel, it goes through symmetric and asymmetric traffic. For example, HTTP, and you may notice inconsistent payloads. For example, covert channel is one of the way for the attacker to hide themselves, but there are other methods as well. For those that attended our class, we talk about connection scrambling, we talk about evasion, and so on, fragmentation, and so on, but this is one of the examples. Okay, so pass it to you.
Hello.
Hello.
Wake up. I myself haven't wake up yet. So I'm going to continue where Spoonfork has stopped. So which is alert data analysis. So basically the alert data analysis, we use the IDS to detect the attacks or decide whether the traffic is good or bad. So it looks for the signs of intrusions and generate alerts based on detection engine. So basically, we like to cover Snort IDS and Bro IDS. So how many of you heard about Bro IDS? Snort? Alright, so apparently Bro is not as popular as Snort. So when we look at Snort IDS is basically utilizing signatures matching engine. Okay, utilized heavily on a signature matching engine, while Bro IDS utilizes its own policy scripts. So if you want to know more about Bro policy scripts, you can actually search in a Bro website. For the Snort, it's a popular open source network intrusion detections and prevention system. So it's commercialized appliance developed by SourceFire. So currently it's 2.x, it's in a version 2.x, and it's going for 3.x, which is having a scripting support. Snort 3.0, they are going to have a lower scripting support, which is just like Bro. Bro by itself supports the scripting, but they use their own policy scripts. So normally, here's a command that you can run if you have the Snort signature rules loaded. And it will generate the alert file, and sometimes the snort.log file, it depends on what you want. It can be a unified form file, or you can be a TCP dump file. So Bro IDS, on the other hand, is a real-time network analysis framework. So, and can be used for pure network analysis. So it emphasizes on the application level semantics, which means that it doesn't really do per packet matching, which means that it doesn't look at, if you heard about ngrab, network grab, it actually do matching on per packet basis. But Bro doesn't do that. It will try to reassemble the traffic so that it will perform the matching. So it has no presumption of good and bad. Good or bad is policy neutral, which means that it does not do signature matching, even though it has the signature matching capacities, but they don't really emphasize on it. So we are not going to talk much about these two IDS. However, you can actually search the website. Okay, search in the website that it contains a lot of information, especially Snort. So we are going towards application protocol analysis. So in here, we are going to introduce things that you might want to look at. Okay, things you might want to look at when performing the application protocol analysis. Because when doing forensics, all we want is actually the files or maybe something that is transferred over the network. So focus on application protocol specification and its properties. Understand widely used protocol deeply. Identify file transfer and extract useful information. So it basically offers deeper insight into attacks and confirm hypotheses created during generic packet analysis. So it can confirm, for example, things like a successful FTP transactions, or maybe there's an attachment in the SMTP traffic. So it confirms successful DNS poisonings and so forth. So to a certain extent, it gauges the skills of the attackers. Like an attacker that uses evasion techniques may exhibit a level of expertise and sophistications. This also indicates a targeted attack, as it shows that attacker is being cautious. So, for example, here is the DNS packet. So this is DNS query. Is a TXT query. The type of it is a TXT. It's a text string query. So you can see here we are using a Wireshark to open it. So if you are going to analyze a DNS traffic, okay, DNS traffic is interesting because it allows you to perform various kinds of analysis. For example, DNS forensics allow you to determine someone's behavior, which most ISP likes to do, because they know where you are serving, website that you are serving based on the host name. So they know they can actually study your behavior. That's what Google doing as well. So basically, if you want to analyze someone's behaviors, so what kind of packet suppose you log? What kind of packet suppose you log and try to collect in order to study someone's behaviors? So DNS is one, but are you going to collect DNS query, or are you going to collect DNS query response? Anyone has idea? So if you want to make sure that the query is successful, that it has a response, so of course we will look at the response, the query response. The interesting part about DNS query is that the DNS response packet always contains the query. So if you want to study DNS traffic, so if you just go for the DNS response, that's enough. Okay, that's enough. So here are some of the examples to analyze the DNS using a TCP dump T-Shark. So basically, it's like you can analyze the UDP traffic using using the Wireshark filters, which is like -R, the capital R, TCP.port equal to 53, or UDP.port equal to 53. So to display the DNS traffic, and for DNS query traffic, you can search for the DNS.flag 0 times 0100. So DNS.flags, that is a particular Wireshark filters. So you may heard about BPF. Anyone of you heard about BPF? Berkeley packet filters. That when you use TCP dump, you are going to use it like TCP dump -R, then .pcat file, then TCP or TCP square bracket 13 close square bracket equal to 2, or UDP IP. Let's say you want to filter out the IP traffic, you just type IP. You want to filter out UDP, you just type UDP. So if we are going to analyze protocol headers itself, like for example, those lower layer protocol like TCP, UDP, IP wise, so you can make use of BPF. Unfortunately, BPF is considered old, and even though it's very useful, but it doesn't allow you to actually dig into certain offset of application traffic, which means that if you want to look for the particular offset in HTTP traffic, you can really use BPF. So that's why we always use these interchangeably by using we are using BPF if we just want to filter TCP, UDP, or IP, or ICMP, but otherwise, if we are going to filter the particular traffic using for application protocol, we are using Wireshark filter. So this one is a HTTP packet. HTTP contains a lot of informations. It contains a lot of informations, especially on client requests and the server response. So to analyze the HTTP, usually we like to look at what contents inside the HTTP traffic. For example, I can use T-Shark, and then HTTP contains cookies to search for the cookies, or I can use there's QZAG HTTP common state to actually look for, to actually shows the statistics of HTTP traffic. So here are the HTTP request methods like get, post, hate, put, delete, trace, options. So these are some of the examples of HTTP request methods. So each methods usually will tell you what this HTTP traffic is about. So the response code itself also will tell you the informations, like if it's about 1xx between 100 to 200 is informational, so 200 is successful. 3xx is redirections. I think a lot of you may face this. And 4xx is bad requests on the client side error, and 5xx is unsuccessful. So these are the response codes written by the HTTP servers for the HTTP request from the client. So common HTTP status code like 200 is okay, and then partial content 206, 30 move permanently, and so forth. So for full list of explanations, so you can read that. In Wikipedia, they have a list of HTTP status codes. So one of interesting thing is that not all successful HTTP attack returns HTTP 200. Okay, for example, in most cases of SQL injections, the return code is HTTP 500. HTTP 500, which may indicate a successful SQL injection attack. Okay, that's because there's the response from the backend, not the web server itself. So the header fields, these are some of the examples of HTTP header fields like accept character set, encoding, language, and content encoding. So a compromised server with covert channel may behave differently. If you look at the HTTP traffic, the covert channels that using HTTP may have different kind of properties. So like, there is a study about the HTTP headers itself. Okay, HTTP headers itself. The arrangements of HTTP traffic, like for example, user agent, host, cookies, and e-tag, right? It may be arranged differently. So maybe like sometimes it's user agent first, then host, but in particular traffic, you'll see host first, then a user agent. Based on different arrangements, so you can recognize different kind of traffic from different softwares. So this one is the part that we always like to look at, which is the content type. So for example, like the content type will tell you that what kind of files are going to transfer, like application/zip, maybe MS Word, JPEG, TIFF, MPEG, QuickTime, octet stream, maybe a binary stream. So by looking at this particular HTTP property attribute, so you can actually recognize that what kind of files are actually transferred. So interesting HTTP headers, user agents. If you heard about emerging threats project that they're actually giving out all the snot rules for free, they always study on the user agents. They have all kinds of the snot rules about the user agent. Different user agent comes from different kind of malwares. So you can actually try to download it and then learn about different kind of user agents. So the interesting part is that if you follow the link from the websites, so they have this example of website that conditionally serving up malicious content depending on the user agent string, which means that now the exploit itself, okay, the malicious code itself will be loaded to particular browsers. So when it sees that, say for example, this is Firefox browsers, so it will load Firefox exploits. So if it's IE, so it will load IE exploits. So it won't simply launch the exploits. So you can decode HTTP protocol as well. And to display it, you can use -t fields -e to display particular HTTP properties like HTTP request methods and so forth. Response codes, user agents, content type, to search for what kind of files it is actually transferred. So the display filter is over in the Wireshark that you can actually search for FTP protocols. So FTP connection methods, there is active mode, passive mode, extended passive modes. So what is active mode? FTP. I think most of you use FTP, right? Most of you use FTP? Yes, no? So what is active mode FTP? Louder? So for the passive FTP, the server will tell the client which port the client can connect to. Which means that if it's in active mode, so client is the main component. He will tell the server what kind of port you can connect to. So on passive, it's different. Passive is the server side will tell the client which port you can connect to. So in the active mode, FTP client initiate connection to FTP server port. The client's port is sent to the FTP server as well, port greater than 1023. So FTP server will respond to the client, and FTP server will initiate a connection from port 20 to the client port. That's the reason why the firewall always block active FTP. Because now if you have firewall here, so now your server is telling the server which port you can connect to. So now is from the server side, you need to go inbound. So most of firewall always block inbound traffic instead of outbound, correct? So that's why passive FTP, on the other hand, server will tell the client which port you can connect to. So client will initiate it. It will connect to the particular port. So that's why it's so fast. All right. So extend. All right. Passive FTP mode. We have like port. The difference between passive FTP mode and extended FTP mode is that the calculations. Okay, the calculations. The extended passive FTP mode in the packet itself, it will tell you exactly like what IP, what port. Okay, but in the passive FTP, not the extended one, basically you need to use the number. It has the high and low byte, so you need to use the high byte times 256. I can't really remember, but times 256, then plus the low byte numbers. Then that is the port numbers of it. So here is the FTP commands: user, pass, delete, store, then store, RMD, retrieve, abort, quit. So looking at these particular commands, you know that what particular FTP traffic is about. For example, if someone store file, means that someone is transferring files. So someone delete files, DLE. So they are retrieving file. So based on the command itself, so it knows list, size, ports, many more. So it has the return code as well. So I have to go through very fast. So here are the return codes. You can refer in the websites, or maybe you can download our slides. So you can also process it. Okay, process using the Wireshark or T-Shark. And here's the SMTP protocol. So most of the slides continuously are actually talking about the protocols and which particular field you should look at when it comes to network forensic, so that you don't you don't do the blind analysis. Decoding SMB protocols, specific tools. So there are specific tools for protocol analysis, like HTTP, you have HTTP-ROI, HTTPS, you use SSL dumps, DNS cap for DNS traffic, TFTP grab for TFTP, and so forth. And challenges in protocol header analysis, blah, blah, blah. Purpose of traffic content analysis. You guys want to look at the demo, or you guys want to read this? Demo? All right. Yeah, you load the VM. So I'm going to show you, how many of you analyze packet data? You show the case. How many of you actually analyze packet data using Wireshark?
So what we have for the training
Case one.
yeah. So what we actually have yesterday for our training was we provided 2 cases.
We are going to show you a free flow analysis, which means that it's free flow, whatever I want to do with the packet data, but based on the case. Okay, based on the case.
So
it's a very quick one.
yeah, the case involved what you call this insider somebody leaking an insider leaking company proprietary sensitive company information, and the students were given a packet trace to work with and try to answer a few questions. So these are some of the questions that was asked, basically identifying the source, identifying the accomplice, who the insider talked to, and what file was transferred from the company, and what's the name of the file, and so on. So okay, this one's there.
So based on the case, okay, based on the case, so you might see that we are looking for the insider who are actually sending the file. So you are given the packet data to analyze. So the packet data itself is case 1. I design the pcap. Let's move it. I move it somewhere so that you guys can see it clearly. So I copy the file first to the case 1 directory. So I have this file, which is case 1-I design the pcap. Everyone can see, right? So first of all, I'm going to verify it. If the file I copy, okay, if the file I copy is actually has the same hash as the file I get from particular departments and so forth. So basically, if the hash is correct, based on the case BF9, FA, based on the case just now, you saw that they offer you the MD5, so you compare the hash, so the data is correct, copy correctly. So now, let's look at the size of the packet you're going to analyze. So it's 77 meg. Okay, it's 77 meg. So it's quite big. Okay, 77 meg is quite big. So let's see 77 meg, how are we going to process it quickly. So if you are using Wireshark, say you are using Wireshark, are you going to load this on the Wireshark and analyze it packet by packet? Are you going to do that? So it will be very slow if you are doing that. So what we do is usually that we are trying to check how many packets we are going to analyze. So the cat info itself basically will tell you the information about this particular packet data. So now we know exactly that the capture duration is about 1000 seconds. So the start time of this particular event falls on 1 o'clock and 29 minutes to 46 minutes. And then the data rate of it. So you roughly have the ideas that you're going to analyze for this particular time. And imagine 46, 29. So the duration of this particular pcap is so short, which means that in so short period, you have 77 meg file to analyze. Imagine you want to analyze gigabit of files. So if I'm going to proceed with analysis, so I'm not going to use Wireshark because I'm not going to look at the packet one by one. So I'm going to have the idea basically what this packet contains, what is the contents of these particular packets. So what I do is that I will try to run this PD states on this particular packet. So from here, you roughly have the ideas, like for example, in this particular packet data, what kind of traffic actually dominate most. So say for example, like HTTP, it consumes a lot of traffic. HTTP, of course, because HTTP belongs to HTTP, HTTP belongs to TCP. So we see that 6532, the traffics. So most of the traffics in a particular packet data are actually HTTP. So if you are the investigator, so you have to set the mindset that most of the data you are going to analyze is web protocols, okay, HTTP protocols. So now you are given particular what we call as the case. What's the case? So case 1, I design a PCAT. So this case has what's the IP address of Chris' machine, what's Chris' non-legitimate email address, and so forth. So now I know most of the traffic I'm going to analyze is the HTTP traffic. So what I'm going to do next is that I'm trying to see what kind of ports are actually has inside this particular packet, so that I know what kind of services I'm going to analyze as well. So in order to do that, so let's say you have a packet data. So let's see, you read it. So here is how, when you read the packet by packets itself. So you can see that there are so many packets. Okay, there are so many packets. So what we need to do now is trying to decrease the time of analysis. So we are going to reconstruct it to session. Okay, reconstruct it to session. So what we can do is that we can convert the data, packet data to session data. So this command basically what it does is that it reads the PCAP and then it writes it to the flow data. So once you write it, so let's look at the size. So the size is 138K. Okay, the size is 138K because the flow itself, here's the flow. So flow data basically gives you the information which is session based, but flow itself is like multiple flows can be in particular sessions. So here it's like you actually drill down the analysis time. So you can see that particular IP connect to what, particular IP connect to what. So what if I construct it to sessions. So let me so I construct it to sessions, and let's see how many lines. So I use WC-L to see how many lines. So it's 215 line. So it means there is about 215 sessions in this particular traffic. But now I'm interested in what kind of destination port. When we talk about port, we talk about network services that are used. If my presentation sucks, right, Amy, I'm going to blame you. So basically, yeah, if you want to know what kind of network services are used, okay, by this particular guy, so we are going for destination port. So what we can do is that we're trying to extract out the destination ports. So let's do it. So this S is to show the particular field in the flow. So you can show just source address or destination address, right? So you can show particular ports. So see so many ports. So what we can do is that we can actually sort it, and then we try unique it. So now you actually have ideas like what kind of destination port are actually connected to. So you have layer 4 endpoints. Layer 4 endpoints, which is port. Layer 3 endpoint is your IP address. So you have the port like 137.138.1.863. So you know like 443 HTTPS is using 1.863 messengers. Is using port 80 HTTP. So you roughly start to have idea what this guy is using. So now I also want to see the IP address are involved in this particular. So there are not so many IP that are in the source address and destination address. So a lot of destination address. So from here, let's say you see the source address. So here are the source address in particular packet data. So now you have a layer 3 endpoint, you have layer 4 endpoints, so you know what IP you are going to look at and what port you are going to, what kind of services you are going to look at. So since HTTP dominates most of the traffics, and it has other traffic as well, so maybe we should look at other traffics. So if you want to look at other traffics, we can do things like I'm going to filter it. So I have this packet data, so I'm going to filter it to no HTTP. Okay, I'm going to filter it to not HTTP, and then not port 80. This is BPF filters. Okay, this is BPF filters, so that I don't want the port 80 traffic. I just want to look at others. So I have like other traffics. Let's look at other traffic size. Of course, in the time of analysis, you must write down, okay, you must have the case notes. So it's only 247K. So I prefer to just load this first. So I load it to Wireshark. Because it's very small size, it's even less than 1 meg, so it's easier for us to analyze. And all of them are non-HTTP. So you can see there's a DNS. This is the DNS. And then most of the traffic are actually from 229.185. If we take out not DNS traffic, so apply. So basically you don't want to see the DNS traffic as well. So now you can look at what kind of, this is UPnP. So go down, you can see like this MSN messengers traffic. So maybe we can see what kind of information. So we can see that here is a CMLong. This is cmlong@gmx.com. This is the email of the particular guy in the company. He's the suspected insider. So 192.168.29.185, that's his IP address. So he's talking via messenger. Okay, he's talking via MSN messenger. So it's usually easier for you, okay, to trying to look at the outline, the macro view of particular packet data before you actually dig into it, okay, and look at packet by packet without having a clue. Okay, without having a clue. Here is just a simple free flow analysis. Okay, we are trying to show so that you can actually trying to reduce the time of analysis. Okay, I have the alarm 16-minute overrun.
Thank you very
why
much.
not just
Ibu.
buffer overflow? 60-minute buffer overflow?
Indeed, very much so. But as you can see, ladies and gentlemen, they've got a lot of materials and they will be around throughout the whole conference, these 2 days. Please feel free to approach them. And I'm sure they'll be more than happy to share more details with you. And again, Mel, CS Lee, thank you very much for your presentation today.
Right. Thanks.
Everyone, we will now adjourn for lunch. If you look at the agenda, it does say we will resume at 1:30. In order to ensure that we maintain on schedule and we don't end too late today, we will commence at 1:30. And hopefully, and I apologize for the short period of time, but you know who to blame, and hope to see you back here at 1:30. Thank you very much.